Hey there, math fans. Going to do the math part. Please watch my previous video first. I was measuring the height of these three things on campus, mostly to give an introduction to calculus in height and velocity, but I wanted to give a little bit of math here. So ultimately, for those people, these are more for my calculus students from previous quarters, and I might have one follow-up where it's more for my current calculus students. But my calculus students know that we start with acceleration. And if we're working in feet, which I was for this problem, it's negative 32 feet per second squared. And that means that's the second derivative of the height function. And so the first derivative, or the antiderivative, we say, is negative 32t plus some constant. And the height function is antiderivative of that, which is negative 16t squared plus ct plus d. Now, for those people in my current class, we're working initially this way, so that part you wouldn't have known. But my thought process on the problem was this: if you have an object that starts at the top and is dropped, so that would be when the tennis ball is at the very top here. Let's pretend that the whole thing starts there, and that's like time 0, let's say. So let's say at time 0, you're at the top, and your velocity is 0. In which case, that means that this is 0. Now, a physics student would say this in a different way, but I'm doing this from a perspective of we don't know any physics. We just know a little bit about calculus, and I'm trying to introduce these calculus ideas, so bear with me, those physics people. D is your starting height, which is the thing we're trying to figure out. But what do we know? Well, we've done this measurement. We've measured how long it took to go from here all the way back down. Now, the first time I did this in my notes, I called that a capital T. And that would be the time, basically from hand to hand. Time from throw to catch. That's the thing I measured. That was this number. Which, in order to get accurately, I had to slow it down. You definitely could make the case that this is not the most efficient way to measure the height. But I sort of like this, that if you're walking around with a ball and just wanted to eyeball the height of something, you could throw the ball there. If you had a tennis racket, you could get a much higher thing, which I'll probably do in a follow-up video, because I can hit a tennis ball really high. I played college tennis, so I'm wondering how high I can hit it. I've never actually done that calculation, so that's another video. But anyways, this time on the way down is half as much as this time. So if the total time here was 2.83 seconds, then the time to come down is half of that this time. And so what I realized was, okay, if I plug in t over 2, which is half the time, into this, I will be at the ground. And the ground is a height of 0. So from that, I got the following. T over 2 squared plus d equals 0. The goal is to find d, and so I got 16 t over 2 squared. And then I simplified that, and it was 16 t squared over 4. So it's 4t squared. And then I went, well, that's a little hard to remember. And I had this clever idea of saying 2t squared. I just rearranged it. So that's the Dr. Loveless method for finding the height of something. Throw a ball up, catch it, and the distance from your hand to the top, provided you threw the ball so it reached about the top, is going to be twice the time from throw to catch, then squared. And so I thought that was pretty cool. I don't think I'd ever heard that before. I don't think it's that exciting, but it's exciting for me because I'm a goofball. But, you know, what that means is if it takes 1 second to go from throw to catch again, then the distance from your hand to whatever you threw is going to be 4 feet because it's twice that squared. If it's 1.5 seconds, so you could almost do this in your head, 1,001, okay, 4 feet. If it's this, it's going to be 1.5 times 2, so it's going to be 3 squared. It's going to be 9 feet. So if it takes a second and a half to throw and catch, 9 feet. I just found it interesting. I never really had encountered this before. 16 feet. That's from your hand. Now, when I released this ball in these problems, I think the first one I had to really throw it hard, so I probably released it from like 7 to 8 feet. I even jumped a little bit, which is amazing that I could get all this weight off the ground. These other ones, when I threw it, it was much smaller. And if you didn't watch my first video, you should watch it. I show these videos of me throwing it. Here's the one where I actually get off the ground. It's embarrassing. I mean, I was surprised that I actually could get off the ground. Look at that. I had a student over here that unfortunately saw me doing this and came and talked to me. And I did it many times. And this was after about 5 or 6 times that I actually threw it hard enough to get close. I realized that was a pretty far one. You can see I had to jump. And I still didn't quite get it there. It's hard to throw underhand like this. I realized after the fact that I should have just thrown it overhand, but it's more fun to see me catch it and throw it. It's hard to throw overhand straight up. Okay, that's it. That's really the thing. Now, what I did to try to make this into a problem I could graph in Desmos is I went back here and I said, okay, what is the velocity at which I hit the ground? So the velocity at which you hit the ground would be the velocity at time, the same time t over 2, which would be negative 32 t over 2, which would be negative 16 t. That's the velocity at which it hits the ground, which is also the velocity at which I'm throwing it because of symmetry and because I'm ignoring air resistance. That's beside the point. The point is, if I wanted to describe the ball from the beginning, the formula is this: t squared minus 16t times little t. And that's the formula for the path of the ball, where I basically insert here the 2.83. And I'll show you that. I did that in Desmos here. And that's all I did here. I took whatever time that was, the 2.83 seconds, and I threw it into Desmos, and that was that formula. I'll share this in my video link. And then I separated the time with the x. X is the actual thing. If I push play on that, it plugs in all the input values from there to there. Let's have it repeat. And it's a pretty good model. Uh-oh, I did the wrong one. 2.83, I said. This is the one I want to animate. This is the one I was trying to mess with. So there you go. But the real point was then the derivative of that. So for that example, if it had been, for example, 3 seconds, you would have had h of t is negative 16t squared. Oh, this should be a plus, darn it, because I'm throwing up. I'm throwing up. For that path. No throwing up. So anyways, if this had been 3 seconds from throw to catch, this is going to be negative 16t squared plus 48t. So let's just see that picture as an example. So I think I'll do a follow-up video on that. So if I'm going 3 seconds from throw to catch, it's so fast. If you try to make it close to it, it goes up 36 feet, that ball. I mean, the actual path of the ball will look like this. Oops, I have my label still going. That's what the ball looks like. But if I label the time, it looks like this. That thing there. Okay, so when we study the derivative of that thing, which is what we're going to be finding, it turns out there's a very easy way to find it. And those of you that have taken calculus, you know that there's certain shortcuts. Let me pause that. And that's what we're going to be learning in Math 112 is these very quick shortcuts for how to take the derivative of this. We'll learn that the derivative of that is 1, the derivative of this is 2t, and this will become second nature for anyone taking a calculus course. And then we'll say the velocity is negative 32t plus 48. But the interesting question will be setting that equal to 0 and finding the time when the ball was at the top. That's the sort of stuff we're doing. These measurements I did was just trying to get some realistic numbers. I wanted to give something physical so you could actually attach your brain to something real. So there you go. That's the Dr. Loveless height measurement method. And it was just a small bit of calculus right here. Realizing that the time from hand to hand, from throw to catch, if I divide that by 2, it's going to be the time from dropping from that height. And then I rearrange it to realize double it, square it. Nice little rule. Okay, I'm sure it's been said before, but if not, I'm going to coin it the Dr. Loveless tennis ball measurement rule. Boy, that really rolls off the tongue. I should add a few more words to it. All right.